You're sitting inside an aircraft at 35,000 feet. Outside, the sky suddenly turns white. Lightning has just struck the plane you're sitting inside. For a fraction of a second, an enormous electrical current is interacting with an aircraft carrying hundreds of passengers, sensitive electronics, and thousands of liters of fuel. And yet, the aircraft keeps flying. In fact, commercial passenger aircraft are struck by lightning far more often than most people realize. So when lightning hits an aircraft, where does all that electricity actually go? A lightning strike isn't simply a ball of electricity that enters the aircraft and disappears. Typically, a lightning channel attaches to one part of the aircraft. As the aircraft continues moving through the electrically charged region, the attachment can change across the surface. The lightning current is carried through conductive paths in the aircraft structure before leaving from another point. The exact route varies from strike to strike, but the important idea is simple. The aircraft is engineered to provide electrical continuity and controlled conductive paths. And that brings us to the part that matters most if you're sitting inside. Why doesn't that current travel through you? The basic principle is similar to a Faraday cage. In a traditional aluminum aircraft, the conductive structure helps carry lightning current through the aircraft's exterior structure, while the cabin remains protected inside. But modern aircraft created a new engineering problem. Many aircraft now use large amounts of carbon fiber composite material. Carbon fiber structures do conduct electricity, but not in the same way or as effectively as traditional aluminum aircraft skin. So engineers add dedicated lightning protection features. These can include conductive metal mesh or foil integrated into the outer layers of the composite structure. The goal is the same: give the lightning current a controlled conductive route and keep its effects away from the people inside. But passengers aren't the only thing engineers have to protect. An aircraft's fuel system needs special protection because even a tiny ignition source in the wrong place could be dangerous. So lightning protection isn't just about the outer skin. Engineers control electrical bonding between structures, protect joints and fasteners, and design the fuel system to prevent lightning effects from creating an ignition source. Critical electrical systems face a different problem. Even if the main lightning current follows the aircraft structure, the rapidly changing electromagnetic fields associated with a strike can induce unwanted voltages in wiring and electronic systems. So aircraft use combinations of shielding, bonding, protected wiring routes, and surge protection. And critical functions are designed so that a single failure does not automatically mean losing the aircraft. None of this is left to assumption. Before these systems are trusted in the sky, engineers have to prove that they work. Lightning protection has to be demonstrated through engineering analysis and testing. Aircraft structures, components, and electrical systems can be subjected to tests designed to reproduce the effects of lightning. Engineers can inject high electrical currents into structural test articles. They can test composite panels. They can examine whether dangerous sparking occurs around fuel system components. And they can test whether electrical and electronic systems continue to perform their required functions after exposure to specified lightning effects. The objective isn't necessarily to make every lightning strike leave absolutely no mark. A strike can leave localized damage that requires inspection and repair. The objective is much more important: to ensure that the safety of the aircraft is not compromised. So when lightning strikes your aircraft, survival isn't a matter of luck. The structure provides conductive paths for the current. The cabin is protected inside. Fuel systems are designed against ignition hazards. Electronics are protected against the direct and indirect effects of the strike. And the entire protection system is analyzed, tested, and verified. The flash outside your window might last only a fraction of a second, but surviving it safely is the result of decades of engineering hidden beneath the aircraft's skin. Because the most impressive engineering isn't always the engineering you can see. Sometimes, it's the reason nothing happens at all.